Hi, this is Alex from devstories.eu. PyTorch Fundamentals, episode 11 of 18. Writing custom forward methods for every neural network quickly becomes tedious when you are just stacking standard layers. You do not always need to manually route data from one function to the next. Sometimes you just need to snap layers together like Lego bricks. That is exactly what the nn.Sequential container does. The nn.Sequential container is an ordered pipeline of neural network modules. When you pass data into this container, the data flows through the internal modules in the exact sequence they were added. Think about assembling a standard 3-layer multi-layer perceptron. Normally, you would define your linear layers and activation functions in an initialization method, then write a custom forward method. In that forward method, you would explicitly take the input, pass it to layer 1, wrap it in a ReLU activation, pass that result to layer 2, apply another ReLU, and feed that to the final layer. With Sequential, you bypass the forward method entirely. You instantiate the container and pass your modules directly into it as arguments. You provide a linear module followed by a ReLU module, a second linear module, another ReLU, and a final linear module. PyTorch automatically handles the data routing. The output of the first module instantly becomes the input to the second, proceeding automatically down the chain. This container is highly efficient, but it has a hard limitation. It is strictly for linear, straight-line data flow. It cannot handle complex architectures that require branching, multiple inputs, or skip connections. If you are building something like a residual network where data bypasses certain layers and gets added back in later, Sequential will not work. For any nonlinear topology, you still must write a custom module with a dedicated forward method. Once you have changed your layers together, you often need to inspect what you just built. Every layer in your Sequential container is a subclass of nn.Module, which means PyTorch automatically registers and tracks all the underlying state. To view this state, you use the named parameters method. Calling named parameters on your model provides an iterator over all the weights and biases inside. Each item it yields is a simple pair, the name of the parameter and the parameter tensor itself. Because you used a Sequential container without explicitly naming your layers, PyTorch generates numerical names based on their index. You'll see names like 0.weight for the first linear layer's weights, or 0.bias for its bias terms. The accompanying tensor contains the actual numerical values, the shape of the matrix, and whether it requires gradient calculation. Looping through named parameters is the standard way to verify your architecture. You can quickly print the size of every weight matrix to confirm your input and output dimensions align perfectly across the entire chain before you ever start pushing real data through the system. The true power of the Sequential container combined with parameter tracking is that PyTorch absorbs the bookkeeping for state management and data routing, leaving you to focus entirely on the shape of your network. That is your lot for this one. Catch you next time.